this video, we're going to look at the oxidation of alcohols to ketones, aldehydes, and even carboxylic acids. This is a good time to look at the oxidation of alcohols because essentially an oxidation reaction can be thought of as a modified elimination reaction. Recently, we've been looking at elimination reactions, and of course, in a single-step elimination reaction, a base will pick up a proton. The electrons that are making the bond between the hydrogen and the carbon will then be used to make a pi bond, and a leaving group leaves. This, of course, is known as the E2 elimination reaction. Now, in terms of terminology here, we usually refer to the carbon that has the leaving group as the alpha carbon. Next door, we have the beta carbon, and the hydrogen that's removed is a beta hydrogen. So in a similar fashion, for the oxidation of an alcohol, the idea is that the oxygen of the alcohol will gain a leaving group, and I will show you a couple of mechanisms by which a leaving group can be attached. Once a leaving group is attached, then we can have the so-called elimination reaction. So you'll see this involves a base picking up a proton. The electrons that are holding that proton to the carbon are then used to make a pi bond, and leaving group leaves. Now, the terminology can be a little bit confusing in the sense that the carbon that is making the bond to the oxygen is normally thought of as the alpha carbon. And so we're removing this proton from the alpha carbon. So maybe rather than refer to it as a beta hydrogen, how about we call it a beta-like hydrogen, because it is on an alpha carbon. So a beta-like hydrogen will be removed. As a result, we'll form the pi bond between the carbon and the oxygen, and in this case, we're making a ketone functional group. Now, just to make matters worse, in the ketone, the alpha carbon is actually considered to be the carbons on either side of the carbonyl. So it can be confusing. If you've got a carbon with a leaving group, that's the alpha carbon. If you have a carbon with an alcohol group, that's the alpha carbon. And then the alpha carbons in ketones and aldehydes are the adjacent carbons. The hydrogen that's removed in the oxidation reaction will be a beta-like hydrogen. Now, why is this thought as being an oxidation reaction? So one of the things that you'll see in the alcohol is our alpha carbon is making one bond to an oxygen. Whereas if you take a look at the ketone, and I'm not going to call it the alpha carbon, but the carbonyl carbon here is making two bonds to, in this case, an oxygen. Right? It doesn't matter actually if it's the same oxygen or different oxygens. It's the fact that it's making two bonds to an oxygen. Now, in first-year chemistry, we often talk about redox reactions from the perspective of the loss and gain of electrons. But in organic chemistry, we focus mainly on what's happening to a particular carbon and how many bonds is it making to a heteroatom. Now, that heteroatom is often an oxygen, but it can also be a nitrogen. We do say that the alcohol has, in a sense, 1 degree of oxidation, whereas the ketone or the aldehyde has 2 degrees of oxidation. So this is an oxidation process. And in many ways, following oxidation reactions in organic chemistry is easier because you're just looking for the number of bonds that that carbon of interest is making to a heteroatom. So let's review a little bit the different oxidation states in connection to the different functional groups that we have in organic chemistry. So at the top here, I'm starting with a primary alcohol. Okay, and indeed, I can call that my alpha carbon. This is a primary alcohol. And if we oxidize a primary alcohol, the first step will be to oxidize it to an aldehyde. Now you'll see here that the aldehyde is still making one bond to a hydrogen, and that will be significant as we go along. But indeed, it's in a more oxidized state because effectively the carbon of interest is making two bonds to an oxygen. And maybe for the purpose of notes, how about we'll just highlight here one bond to oxygen. Here we'll say two bonds to oxygen. And then finally, if you take a look at the carboxylic acid, this is a more oxidized state where the carbon of interest is making 3 bonds to oxygen. In fact, if we take carboxylic acid and oxidize it further, we can change the carboxylic acid to CO2. And this is the most oxidized state of the carbon. And in many ways, what happens in our own bodies is to take a more reduced form of carbon, either in the form of fats, carbohydrates, proteins, and oxidize the carbons that are involved to higher oxidation states, whether that be alcohols, aldehydes, ketones, ultimately carboxylic acids, and then finally carbon dioxide as a byproduct. So this oxidation series is a very important kind of concept in organic chemistry, but also in our biological systems. If we take a secondary alcohol, which is this guy right here, we can see that that secondary alcohol can be oxidized to a ketone. And in fact, it cannot be oxidized any further than the ketone, no matter what kind of oxidizing reagent that we use. Once again, we're starting with one bond to oxygen, and then finally here we have two bonds to oxygen. And if we start with a tertiary alcohol, no matter what reagent we're using, we cannot oxidize it any further. So that'll be important that you connect that primary can ultimately be oxidized to a carboxylic acid, secondary to a ketone, and tertiary cannot be oxidized any further. Now, you might at first think, oh dear, I've got to memorize this, try to keep it straight. But actually, it's kind of easy because what you're looking for are removable hydrogens. If we take a look at our primary alcohol, we see that the alpha carbon, in fact, has two removable hydrogens. If we take a look at the aldehyde, and I already circled this in purple, I'm going to circle it in red now, that has one removable hydrogen. So the primary alcohol can be oxidized further. The aldehyde can be oxidized further. Ultimately, normally the carboxylic acid in terms of organic chemistry is considered to be the most oxidized state. Now, starting with our secondary alcohol, you'll see here that we have one removable hydrogen. And so if that secondary alcohol is oxidized, well, then we'll end up with the ketone. The ketone, of course, is surrounded by two carbons. There are no removable hydrogens, so the ketone cannot be oxidized any further. So we're looking for removable hydrogens. That will be the key, in a sense, to be able to predict if something can be oxidized further. Now, you might be wondering, well, what the heck do we mean by removable hydrogens? Well, one of the things is, if we take a look at the mechanism, you'll understand how having this removable hydrogen is important for the oxidation process. And essentially, this is the beta-like hydrogen that can be removed in an elimination-like process. So let's meet our two, what we'll refer to as strong oxidizing agents and the corresponding mechanism. So the first strong oxidizing agent that I'd like you to be familiar with is bromine in the presence of sodium hydrogen carbonate, or essentially baking soda. So I say here the reaction with bromine. The other reagent listed below in the over the arrow notation is the sodium hydrogen carbonate. And normally, usually, this is done in the presence of H2O. So if it's not done in the presence of H2O, we would say anhydrous, and that will have a certain outcome in these oxidation reactions. So one of the things that I wanted to remind you is, in order for this to be like an elimination-like reaction, we need to have a leaving group attached to the oxygen that is our alcohol. So here we have our primary alcohol. This is the alpha carbon. And essentially, the first step is the alcohol group is going to pick up its leaving group. And as you know, bromine is an excellent leaving group. Okay, so that's the first step. The next step is the deprotonation as a result of having an additional bond of the alcohol oxygen. So we have this deprotonation, and no longer do we have a formal charge. And now we're ready for the elimination process. So while this is our alpha carbon, we have a beta-like hydrogen that can then be removed. So it'll look like the following. And do keep in mind that it's the bromine that's our leaving group. So maybe you even might want to start with that. So we have a picking up of this proton, forming of a pi bond, and the loss of the bromide. So that's the oxidation process. And we can see this results in forming the aldehyde. The aldehyde, of course, is now making two bonds, or effectively two bonds to an oxygen. That's a more oxidized state. Now, here's one of the things. We consider the bromine in the presence of sodium hydrogen carbonate to be a strong oxidizer. And so the consequence for this is, normally we're not going to be able to stop the reaction just at the aldehyde. It will be oxidized further. I will show you this in the context of the next oxidizer, but the conclusion also applies to our bromine in the presence of sodium hydrogen carbonate. And essentially, it's the same mechanism, just involving these particular reagents.